Jnanam Paramam Dheyam. Knowledge is supreme.
So today what I'm going to do is, I'm going to take you a fast track on whatever you've learned in your first year, so that you know there is some kind of a continuity and you will appreciate further. Okay, so whoever has learned already, it may be a little bit repetition, but it's good to go over this repetition once so that you are all with me. Okay, so review of particle in a box, potential well, barrier, step potential, harmonic oscillator is the theme for today. And slowly I'll take you on to the delta function and some of the properties of one-dimensional problems, bound states, scattering states. Particle in a one-dimensional box, all of you, even in the middle of a sleep, I'm sure all of you know now. Is that right? What is it? You put an infinite potential at two coordinates in one dimension at x equal to 0 and x equal to 0 and x equal to L, and inside the box you treat like as if it is like a free particle. It's not exactly a free particle because it's bound by these kinds of potential, it's constrained. So what is the wave function of such a particle? You have tried to evaluate using time independent Schrodinger equation, right, and found that the wave function which satisfies the time independent Schrodinger equation, the normalized wave function is root of 2 over L times n sin n by x square. Everybody has derived this. I'm sure you have done it enough. If you have not, if you don't remember, please go back and take a look at it. Okay. And the corresponding, once I say solution to time independent Schrodinger equation, what does it mean? You have to give both the wave function as well as the corresponding energy eigenvalues. Okay. So the ENs are the corresponding energy eigenvalues, and they are also discretized, integer multiple n squared, multiplying a common factor which is pi squared h cross squared by 2mn L squared. L is the length of the box. So this is what we mean by a solution to a time independent Schrodinger equation. Okay, for a particle in a box, you put in these conditions in the derivation, and then you recall the Schrodinger equation, substitute the fact that u of x, I of x is tending to infinity, right, because u is tending to infinity. So this is something you need to worry. So then you find the solution by setting the wave function to be 0 at x equal to 0 and x equal to L, and wave function has to be continuous, right. So this is something which I said even in the last lecture, that wave function has to be continuous even for infinite potentials, but derivative of wave function will not be continuous. This is something which I stressed in the last lecture. So once you put this in, we need the wave function to be only continuous, no derivative, and inside the box you put u equal to 0 in the time independent Schrodinger equation. This is what I was saying, and the most general solution is a linear combination of sine and cos, and imposing that k is proportional to square root of the energy. And at x equal to 0, you want your wave function to vanish, and that forces you to make d to be 0. This is the way you went through the derivation. Similarly, at x equal to L, you can try and show that it will be again 0 if the k is quantized in this fashion, KL equal to 10 pi. So once you use this, you see this one thing, when u is 0, the particle is like the free particle, right? But if you put the free particle with some kind of a constraint, putting a constraint as potential is infinity at x equal to 0 and x equal to L, the K, which would have been continuous for a free particle, is no longer continuous. It becomes discrete. The K, which is given here, KL equal to n pi, where K is n pi by L, that discretization is happening because of the constraint which you have put in, that the particle cannot move beyond x equal to 0 and x equal to n. Okay, this is the first feature which you see for a particle which almost looks like a free particle, but not actually. It is constrained with the potential being 0 and infinity. If it was not there, what will be the form? K can take any value from minus infinity to plus infinity in continuous fashion. You agree? So this K being discretized is because of putting this constraint that it cannot move beyond x equal to 0 and x equal to L. It has to move only between x equal to 0 and x equal to L. Is that right? So discrete values start showing up if you start putting in such kinds of bounds. Infinite potential boundaries, if you start putting in, then you start seeing that the energies are no longer continuous. It becomes discrete. So you can't have arbitrary energies like free particle can have from minus, all possible energies, positive values from 0 to infinity in continuous fashion. Here you will have the energies to be discretized and only selective values. So these are quantum features which you wouldn't have seen in classical physics. If I give you a free particle, you will write P squared over 2m and say that P can take minus infinity to plus infinity in continuous fashion. Now you cannot see that. Okay. So you can put in these quanta, just like the Planck way of writing. You can define one unit of quanta to be this pi squared h cross squared by 2ml squared. And then you can rewrite all the allowed energies for a particle in a one-dimensional box as n squared E naught. So En is now discretized with quanta n squared multiplying E naught. So not all energies are allowed. Energies which are allowed are in the series. Somebody asks you whether 2E naught can be found in the spectrum. No. 3.2 E naught? No. And so on. So you can start saying forbidden energies are these. Such things you cannot say in your classical physics. This is why the Bohr's orbits were very specific. You can't go somewhere in between. You have to be in one stationary orbit to go to the other stationary orbit and so on. Okay. This normalization fixing depends on your domain of integration. Here the wave function is non-zero between 0 and L. So you need to put this normalization condition and fix the normalization. So these things I'm sure you have done it in your first year course. And once you have that, you have the final wave function which I had it in my first slide as this, and the corresponding energy is quantized as n squared E naught, and the lowest energy is n equal to 1 and not n equal to 0. So the wave function is psi 1, n equal to 1 is the lowest energy level, corresponding energy is E1 which is equal to E naught, and the wave function is psi 1 of x. And n greater than 1 are the excited states. And what is the average value of position, also called expectation value? This also we discussed last time. Formally it is psi star, the operator x, psi, evaluated. These things, these integrations you can do and verify that the average value of the position is L by 2. And you can also plot wave functions. It's a sine function. You can plot what is the expectation value of x and so on. Okay. So far we did one-dimensional box. If we make it into a two-dimensional box, what is the modification? You have x and y axis. Okay. And the particle, we are taking a square box. We could take a rectangular box also if you want, but just for simplicity, let's take a square box. So the diagram explains where the potential is infinity and inside the square box it is 0. So what do we have to do? You have to first write the Schrodinger equation in 2 dimensions, then separate wave functions for potential energy, separable wave functions. If your potential energy cannot be written as sum of a potential energy for x plus sum of potential energy for y, then separable wave functions is not applicable. I'm sure you know this, right? So separable wave functions, at least this particle in a 2-dimensional box falls into this class where u of xy is 0 for all x and y which is less than L, right? Between 0 and L, if x and y are taking values, u of xy is 0 and you can treat this condition being satisfied. So you can do separable wave function. And then we look at the solution of particle in the 2-dimensional box. So 2-dimensional Schrodinger equation is again time independent. You earlier had only a del squared by del x squared in particle in a 1-dimensional box. You will also have a del squared by del y squared term. So that's the first step, and psi will be a function of both x and y. And normalization condition will involve not just integration over x, should also do an integration over y, right? It's now a 2-dimensional problem. Straightforward extension. So this is what is it. So you can put the limits as 0 to L and 0 to L for the particle in a 2-dimensional box. If the potential energy is u1 of x plus u2 of y, then I can write the above equation, the top equation, as an operator O which depends only on x and another operator which depends only on y, and act it on psi of xy. So this is the main theme in your differential equations. If you can split the differential operators which depends only on x and another differential operator which depends only on y, then what is possible? Psi of xy can be written as psi of some kind of a phi of x and some other function of y, right? So that possibility exists only if you can write your differential operator into linear sum of 2 differential operators where one is dependent on x and another one is dependent on y. So the 2 differential operators are these, one O1 which is dependent on only x and O2 which is dependent on only y, differential operators. Sorry, this one has to be, there's a typo here, U2 should be y, just correct it, U2 should be y here, okay. For such separation of potential energy, you can write separable functions. I'm calling it as f of x g of y. Even though I'm stressing on particle in a box, this is applicable for other situations also. This is a formal 2-dimensional Schrodinger equation, how you can separate if your potential energy is a sum of, different coordinates potential energies. So now you substitute into your 2-dimensional differential equation, Schrodinger equation, and divide by f of x g of y, and you will get the piece which is x dependent, put it on the left hand side, piece which is y dependent, put it on the right hand side, and they will be related up to a factor of e. So this is the exact expression. Or equivalently, this plus this will be equal to e, because we have divided by psi, okay. Please check it. So this is just for convenience. LHS is only dependent on x and RHS is dependent on y, and you can equate both of them to be equal to some constant a and solve for the constant, which will again become a differential 1-dimensional differential equation. Solve for f of x, okay. And similarly, you can solve for g of y, which will be the second 1-dimensional differential equation. So we will now solve for the wave function of a particle in a two-dimensional box. What are the things which you see here? First thing which you will observe compared to particle in a one-dimensional box is that there can be two different wave functions which can have the same energy. So that is what is called as a degeneracy. Degeneracy will not show up in a one-dimensional particle in a box. Okay. One-dimensional particle in a box can also be felt as it is a bound state. It is bound inside x equal to 0 and x equal to L. Okay, so this is the first thing which you will observe. So let's solve the solution. Psi of xy, we have justified now that we can write f of x g of y even for particle in a two-dimensional box. And recall the wave function should vanish at x equal to L or y equal to L. That you know, and similarly x equal to 0 and y equal to 0. So put in those conditions on your wave function. What is the form you will get? Inside the box, you have to solve this differential equation. This equation is nothing but your A is similar to your, similar to your K which we did, K squared, no different in one-dimensional problems. Okay. So d squared f by dx squared is 2ma by h cross squared. Call this as your k squared. Here just for simplicity we will call it as kx squared if you want. Okay. And similarly you have the other equation. It's not equal to a but it is e minus a. Is that fine? All of you are with me? Okay, just to summarize, so these are the set of equations. Formal operator equation is written, the explicit form is given in the second line, and then you have a formal operator equation for the y dependence, and the explicit differential operator is given in the second line. What is the solution? Very simple. Sure, all of you know the solution. You can write the first one as f of x as a sin kx plus b cos kx, similarly g of y. So you put a subscript x for the k just to keep track that kx is root of 2ma by h cross squared and ky is root of 2m e minus e by h cross squared. So what is the condition? Kx is this and ky is this. And you impose the condition f of x equal to 0 at x equal to 0 and x equal to L, which will make b equal to 0 and kx will be quantized. Similarly, ky will be quantized and d will be 0. So the combined solution for a two-dimensional particle in a box up to a normalization is a product of two sign functions exactly similar, with one with nx as the integer quantum number and ny as another integer quantum number. Okay. And how do you fix the normalization? You integrate over dx as well as dy because it's a two-dimensional problem, and you can fix the normalization. Is this correct? A prime is root 2 by L or it is going to be just 2 by L? It has to be 2 by L. For each integration there will be a root 2 by L. So this also you should correct. And the corresponding energy for a specific wave function, the wave function here I should put an nx comma ny subscript. For that wave function the corresponding energy will be nx squared plus ny squared. Nx squared will be a squared, ny squared will be e squared minus a squared. So the a squared will cancel. So you get this explicitly that the energy has to be nx squared plus ny squared. Again, you can define a fundamental energy unit and rewrite the particle energies in a two-dimensional box as E naught multiplying squares, sum of squares of two quantum numbers, nx squared plus ny squared. This is an exercise for you. If I tell you that the energy of a particle in a two-dimensional box is 13 E naught, is the wave function unique? What are the possibilities? 2, 3 and 3, 2. So the wave function has nx as 3 and ny as 2. That can also be another wave function with nx as 2 and ny as 3. Both will share the same energy eigenvalue. So that's why these two wave functions are degenerate. In fact, that level, that energy level you will say is twofold degenerate. Symmetry of the two. Yeah, so I'll give you one more thing where you will see an accidental symmetry. One more. Okay. So it happens because of the symmetry of the square, but there could also be accidental symmetry. Okay. So let me try and give you that example. 50 E naught. What are the possibilities? There is no symmetry there. So that could also be accidental degeneracy, because the number adding as nx squared plus ny squared to be some specific value can have so many possibilities. Case of 13 E naught, the symmetry of the square tells you you can interchange nx and ny. That is what he was saying. But when you do it for 50 E naught, not only that symmetry, but you also have accidental things, that you will have nx as 7, ny as 1, that gives you 50 E naught, ny as 7, nx as 1. You also have nx equal to 5 and ny equal to 5. So it's a threefold degenerate. Such possibilities also exist. So case by case you have to find the degeneracy. It's not always twofold degenerate. It can be more than that. That is all I'm trying to say. So I have given you a flavor of doing it for two-dimensional box. It's not difficult to do a three-dimensional box. You first put the y-z dependence on the right hand side, x dependence on the left hand side. Put it to be a constant. And then the y-z you separate it as y and z. Go systematically. So you'll have an f of x, g of y, h of z. And you can write it as a product of three sign functions. Right? So very straightforward exercise. The first, if you understand two dimension, you can get to what happens to degeneracy. The cubical symmetry will allow permutation of nx, ny, and z. The energy will be energy E nx, ny, and z is E naught times nx squared plus ny squared plus nz squared. 3D box. Square box. Or I should technically call it as cube. Okay? Is that okay? So E of nx, ny, nz is nx squared plus ny squared plus nz squared for a 3D square box. You can again work out degeneracies here. And you can also write what is the wave function. X, y, z to be, you can write it as 2 by L to the power of 3 by 2 multiplied by sine nx pi by L multiplied by sine ny pi by L. X is there, right? And then sine nz pi z by L. Is that okay? What will be the modification if you try to put it in a kind of a cuboid with L1, L2, length, breadth, height to be L1, L2, L3? you have to accordingly modify these things. If you do the modification, this E0 is also cannot be written as universal E0. You have to appropriately put a by L1 squared, by L2 squared, by L2 squared. You know what is the. And there is no symmetry in that case, that can only be accidental coincidence of total length. Is that alright? Okay, so the list which I have given is for the two-dimensional box, and then I have said for you to work it out. There will be some assignment problems on 3D box and you can try and fix it. Okay.